Imagine a place of perfect darkness and cold, an immense, silent cloud drifting between the stars. This is not just empty space, it is a nebula, a cosmic cradle, a vast collection of gas, mostly hydrogen, and fine space dust. For millions of years, this cloud rests in a state of quiet equilibrium. But then, something extraordinary happens. Perhaps it is the shockwave from a distant, exploding star, or the gentle squeeze as it passes through a dense spiral arm of our galaxy. This disturbance is the first push, the trigger for one of the universe's most magnificent events, the birth of a star. Gravity, the invisible architect of the cosmos, takes over. It begins to pull the particles of gas and dust inward, toward a common center. As more and more material gathers, the cloud starts to collapse under its own weight. It breaks apart into smaller, denser clumps, each one a potential star in the making. These clumps, known as protostars, are the infants of the stellar world. At this stage, they are not yet stars, they are simply balls of gas, heating up from the immense pressure building within their cores. The collapse converts gravitational energy into thermal energy, and the temperature begins to soar. For hundreds of thousands of years, this process continues. The protostar grows, spinning and collecting a disk of leftover material around it. From this disk, planets may one day form, but for now, all the action is at the heart of the collapsing cloud. The core is getting hotter and denser, preparing for the moment that will define its existence. This cosmic cradle, once a cold, dark void, is now a glowing, chaotic nursery, giving birth to new suns that will one day light up the darkness. We are witnessing the very first chapter of a story that will last for millions, or even billions, of years. The protostar is not shining from its own power yet, it glows with the residual heat of its violent formation. It is a preview, a promise of the brilliant light to come. All the forces are aligning, the pressure is mounting, and deep within its core, the conditions are slowly becoming so extreme that they will soon cross a fundamental threshold. The universe is about to ignite a new furnace, and the quiet cloud will become the birthplace of a shining star. This is the quiet, powerful beginning of an epic journey. Deep within the core of the protostar, a monumental battle is raging. For millions of years, the immense force of gravity has been crushing the material inward, creating unimaginable pressure and heat. The temperature soars to staggering levels, reaching millions of degrees. At these extreme conditions, the very nature of matter changes. The hydrogen atoms, which normally repel each other, are moving so fast and are squeezed so tightly together that they can no longer avoid a collision. They begin to smash into one another with incredible force. This violent collision is the start of a process called nuclear fusion. In these incredible impacts, the nuclei of hydrogen atoms fuse together to create a new, heavier element, helium. This is not a simple chemical reaction like fire, it is a nuclear transformation. In this process, a tiny, almost imperceptible amount of mass is lost. But according to Einstein's famous equation, E equals mc squared, mass and energy are two sides of the same coin. That tiny bit of lost mass is converted into a colossal amount of pure energy. This energy erupts from the core in the form of light, heat, and radiation. The outward push from this nuclear furnace finally balances the inward crush of gravity. This balance is a stellar milestone. The star has officially been born. We have entered the longest and most stable phase of the star's life, known as the main sequence. Our own Sun is a main sequence star, and it has been in this stable state for about 4.5 billion years. For 90% of its life, a star will fuse hydrogen into helium in its core, shining steadily and reliably. The size, color, and lifespan of the star are now determined by its initial mass. A massive, heavyweight star will burn its hydrogen fuel furiously, shining with a brilliant blue-white light but living a relatively short life of only a few million years. A smaller, average star like our Sun burns its fuel at a more moderate pace, glowing yellow, and can last for billions of years. This perfect balance between gravity and fusion energy is what makes stars the steady beacons of the cosmos. They become cosmic engines, tirelessly converting mass into light and heat, making life possible on orbiting worlds. For a star, stability is only temporary. The very process that gives it life, nuclear fusion, also sows the seeds for its eventual transformation. For billions of years, our main sequence star has been a model of cosmic efficiency, steadily fusing hydrogen into helium in its core. But hydrogen is a finite fuel. Eventually, the star begins to run out of hydrogen in its central core. The core, now rich in the ash of helium, can no longer sustain the same level of fusion. This is the beginning of the end of the star's stable life. With the central fusion engine sputtering, the balance of power shifts. Gravity, which has been held at bay for so long, sees an opportunity. Without the constant outward pressure from fusion, gravity begins to crush the core inward once more. This renewed collapse heats the core to even more extreme temperatures. But something new happens now. The area around the core, which still contains plenty of hydrogen, becomes hot and dense enough to start its own fusion reaction. A new shell of hydrogen fusion ignites around the inert helium core. This new, outer source of energy has a dramatic effect on the star itself. The enormous energy output from the shell fusion pushes the star's outer layers outward with tremendous force. The star begins to swell, and it swells enormously. It grows to hundreds of times its original size. It has become a red giant. If our Sun were to go through this phase, its outer layers would expand to engulf the orbits of Mercury, Venus, and even Earth. The star's surface cools down during this expansion, giving it a distinctive red glow, but its core tells a different story. The core, made of helium, is being compressed and heated by the relentless pull of gravity. It is getting hotter and denser, preparing for the next, even more powerful, act of nuclear fusion. The star is no longer the steady beacon it once was, it has become a volatile, aging giant, on the verge of a dramatic and final series of events. For a star like our Sun, the final act is both beautiful and destructive. We left our star as a swollen red giant, with an inert helium core being crushed by gravity. The temperature in the core continues to climb, and when it reaches a staggering 100 million degrees, a new kind of fusion is triggered. In a sudden and violent event known as the helium flash, the helium atoms in the core begin to fuse together. They create carbon and oxygen. For a brief time, the star finds a new, though unstable, equilibrium. This helium burning phase is turbulent. The star pulsates, varying in brightness, and continues to shed its outer layers into space. It cannot fuse carbon into heavier elements, its core is just not massive enough to reach the required temperatures. So, after the helium is exhausted, the cycle repeats. The core, now made of carbon and oxygen, collapses again. A new shell of helium fusion ignites around it, and outside of that, a shell of hydrogen fusion still burns. The star becomes layered, like a cosmic onion. The end is near. The unstable fusion processes cause the star to expel its outer layers completely. These beautiful, glowing clouds of gas are called planetary nebulae, though they have nothing to do with planets. They are the star's final gift to the universe, enriching the cosmos with carbon, oxygen, and nitrogen, the essential building blocks for planets and life. What remains is the star's incredibly dense, hot core, exposed to space. This is a white dwarf. It is no longer performing fusion, it is just a super-hot ember, about the size of Earth but containing nearly the mass of the original star. A single teaspoon of its material would weigh as much as an elephant. It will shine for billions of years from its residual heat, slowly cooling and fading into a cold, dark, black dwarf, the final, silent remnant of a once shining star. This is the peaceful, yet profound, end for stars of a certain size. But what about stars that are much more massive than our Sun? Their fate is far more dramatic and violent. A massive star lives fast and dies young. It races through its life cycle, fusing hydrogen, then helium, then carbon, neon, oxygen, and silicon. In its final days, it resembles a giant onion, with a core of iron and shells of progressively lighter elements. Iron is different. Fusing iron does not release energy, it consumes energy. It is the final ash, the end of the line for the star's fusion engine. When the iron core grows too large, the fusion stops for good. Instantly, the outward pressure vanishes. Gravity wins the battle in a fraction of a second. The core collapses from a size larger than Earth to a ball of atomic nuclei just a few dozen kilometers across, in less than a second. This collapse is so fast and violent that it creates a shockwave of unbelievable power. The outer layers of the star, with nothing to support them, come crashing down onto the rigid core and bounce. This bounce triggers a cataclysmic explosion known as a supernova. For a few weeks, a single supernova can outshine an entire galaxy. The explosion is so energetic that it forges all the elements heavier than iron, the gold in your jewelry, the uranium in nuclear reactors, the silver in your cutlery. All of these were born in the heart of a dying, massive star. The supernova blasts these newly forged elements and the remains of the star out into the galaxy, seeding future generations of stars and planets. What is left behind is the crushed core. If the core is between about 1.4 and 3 times the mass of our Sun, it collapses into a neutron star. This is a city-sized object so dense that a sugar cube-sized amount of it would weigh as much as a mountain. It is a bizarre ball of neutrons, spinning rapidly and often emitting beams of radiation that we detect as pulsars. But this is not even the most extreme outcome. For the most massive stars of all, the final collapse is so powerful that not even the formation of a neutron star can stop it. If the remaining core is more than about 3 times the mass of our Sun, gravity becomes an unstoppable, all-consuming force. The collapse continues beyond the neutron star stage. The matter is crushed into an infinitely small, infinitely dense point known as a singularity. The gravity around this point is so strong that not even light can escape its pull. A black hole is born. The boundary around the singularity, the point of no return, is called the event horizon. Anything that crosses this threshold, gas, dust, planets, even light itself, is lost forever from our observable universe. Black holes are not cosmic vacuum cleaners, they are gravitational pits. From the outside, they are simple, dark, and mysterious. Yet, they represent the ultimate victory of gravity over all other forces in the universe. But this is not just a story of endings, it is a story of renewal. The supernova explosions that create black holes and neutron stars are also the great recyclers of the cosmos. They spew out the elements forged in the star's life and death across the galaxy. These enriched clouds of gas and dust will eventually mix with primordial hydrogen. Then, billions of years later, triggered by a passing shockwave, gravity will begin its work again. A new nebula will collapse, and a new protostar will form. But this new star will be different. It will be born from the ashes of its ancestors. Around it, a new planetary system may form, containing rocky planets rich in silicon and iron, and perhaps, on one of those worlds, the carbon, oxygen, and nitrogen from long-dead stars will come together to form the basis of life. We are, all of us, literally made of stardust. The epic life cycle of the stars is not just a distant cosmic drama, it is our own origin story.